make sure you can hear me. That would be useful. All right. Good afternoon, everybody. So, hopefully, it's okay. Good. Um, I posted, or the TAs posted yesterday an announcement that should have gone out as an email. And you can get to that announcement if it didn't go to you, but you can get to that announcement on Canvas. Um, so basically just gives the office hours. So you've got two TAs, Aiden and Josh. Josh's office hours will be 10 to 11 on Thursday, and Aiden's office hours will be Tuesday, 1 to 2. They also set up a Discord server, so there's a link, not that one, I don't want to accidentally click on it, but there's a link there to join it. Said it expires in 7 days, but you could just shoot them an email and they can add you to that group if you'd like. And it's just a place to, to ask questions and of each other and of the TAs, and just general Thermo 1 merriment. So I'm not really planning on joining. I guess I could, but yeah, I wasn't planning on joining. I just figured it should be a student-led thing. What else? If you scroll down, I did add a couple of buttons down here at the bottom for office hours, and that way you can click and it's oh, thank you, Christopher. I appreciate that. Yeah, so there's a couple of clickable links because they're different. It's different I guess Zoom, I don't know, links for those particular office hours, but that way it's there. So I'm planning on just having my virtual office hours until we come back on the 24th. And I think Aiden and Josh are planning to do them in person once we get back to in person, but just until they decide what they're going to do, I'm just going to keep it as virtual, and then they'll let you know if they're going to change their office hours to in person as well. Okie dokie. So this is where we left off. So hopefully you've had a chance to watch up to video 1.7, and it's pretty loaded videos, and I know it's a lot. It won't always be that much, but it's important to kind of get up and running and being able to read the tables that we're going to start using today. So we'll start by talking about the state principle, which is addressed in video 1.4. And the state principle says, for a simple compressible system, the state of a system is completely specified. That means it's fixed. So when we say fix the state of the system, we mean we know this handful of properties, we can figure out any other property that we want to know, we know what phase it is, that kind of thing. But the state of the system is completely fixed by two independent intensive properties. So independent, intensive properties. So a couple of words in there. So compressible, from our standpoint, it means that the specific volume or the reciprocal of that, the density, that's rho, that's not pressure, but the density or the specific volume can change for a given process. Sometimes we model things as incompressible, like fluids or solids, something that's like liquid. We can model that typically as an incompressible substance. But so a compressible substance, you're going to need two independent intensive properties. So independent, kind of self-explanatory. If one of those properties changes, the other property doesn't necessarily change. And then intensive. Remember, this is means that particular property. So we're talking about a type of property, but it's a property that's independent of size or mass of a system. So, at this point, we know a couple of intensive, or actually, we'll say properties. So we've got temperature. We talked about temperature, pressure, volume, specific volume. And it's these guys that are the intensive properties. So as far as, if those three properties, figuring out, okay, well, they're all intensive, but when are they independent of one another? Temperature and pressure, or temperature and specific volume, are always independent of one another. And so if you know those properties, if you know temperature and specific volume, you know right away that's enough information to fix your state. It's enough information to figure out any other properties that you want to know about the system. And of course, at this point, we only know temperature. The intensive properties that we know or are familiar with are temperature, pressure, and specific volume, but that won't always be the case. We'll be introduced to other intensive properties as well. All right, so temperature and specific volume, always independent of one another. So that's always going to be enough to fix the state. Same thing with the pressure and the specific volume. They're always independent of one another, so it's always going to be enough to fix this, fix the state. The temperature and pressure are independent in a single phase only, i.e., not in the saturated region. Let's talk about what that saturated region is. Watched the video where you read the readings that kind of go along with this. In your book, there is a three-dimensional representation of how temperature, temperature, pressure, and specific volume are related to one another. I think the figure that's in your book is for water, and typically we deal a lot with water. So, but there are the things that we're going to be talking about apply to other substances as well. It just, we happen to deal a lot with water in this class. So you have this 3D representation in your book, but that's a little bit clunky to use or draw on a two-dimensional format, a piece of paper. And so what we do is we do a projection of two of those properties onto a diagram like this. So temperature and specific volume, and pressure and specific volume. And these domes that I've drawn here, this is the liquid vapor dome. So anything that is underneath the dome, this is two-phase or saturated. So if whatever substance that you have, if it happens to be at a temperature and pressure or a specific volume and a temperature and specific volume or pressure and specific volume, right, these particular coordinates, if it happens to fall on or under this dome, then it's called saturated. So within that saturated region, it's a phase change, and this is the phase change between a liquid and a vapor, and that's kind of where we stick with in this class. Just the applications that we're interested in typically are liquid, gas. It doesn't mean that we couldn't also talk about solids, but we just don't talk about it too much in this class. All right, so with that being said, we're interested in the liquid and the gas phase. So anything kind of to the left of that vapor dome is in a liquid phase. And in this class, like to call things special names. So instead of saying it's a liquid, we say it's a compressed liquid, or maybe a subcooled liquid. So compressed or subcooled liquid. And then it's over here, we've got a gas. But we don't just call it a gas. I mean, we can, but when we're dealing with something that's kind of close to that that vapor region, or that yeah, that vapor dome, then we call it a superheated vapor. It wouldn't be incorrect to call it a gas. That would be fine, but it's just what you'll hear it referred to as, so superheated vapor, especially when you're talking about water. All right, get a little bit more specific. So anything that's on this line, that's on the kind of the left-hand side of that dome, if it falls right on that line, we give it a special name. Call it, and I'm going to kind of zoom in here so I can write it. It's on that line, we call it a saturated liquid. And a saturated liquid is something that is still, it's 100% liquid, but it's about to boil. And that's what happens under that dome is you have two phases that happen. You have saturated liquid that's just about to boil, and then you've got the liquid that's already boiled, and that's your saturated, not superheated, but saturated vapor. And that saturated vapor, just like, we kind of defined everything that's sort of on the left-hand side of that dome. Well, if it falls on this guy on the right-hand side, that's a saturated vapor. Okay. And similar definition, right? It's 100% gas, but it's about to go into that two-phase region, not boil because it's already a gas, but it's about to condense. All right, and it's the same, the same regions over on that PV diagram, right? Anything along this line right here, that's a saturated vapor. Anything that's on, this left-hand side, that's a saturated, or anything that's on the line, I should say, on the line, we designate as a saturated liquid. So a saturated liquid versus a subcooled or a compressed liquid, if you look at it, it looks the same. It's still 100% liquid, but because it's on that tipping point, it's about to boil, we give it a special name. It's a compressed or a subcooled, or I'm sorry, it's a saturated liquid as opposed to a compressed or a subcooled liquid. All right, and we just wrote already that region of saturation, or the two-phase region, it includes both things, saturated liquid and saturated vapor. Okay. All right. Now, just because we're only looking at two properties on each of these, like for the TV diagram, we've just plotted temperature and specific volume data, right? So at these particular temperatures and specific volume coordinates, if you will, the substance that you're looking at, let's say water, exists as a liquid or as a gas or as a saturated substance, right? It's boiling or condensing, but it's going through a phase change between a liquid and a vapor. However, that pressure data didn't go away, it's still there, right? And same thing with the PV diagram, we still got temperature data, it's just not on there. But if we could sort of project that pressure data on here, I could also draw lines of constant pressure on here, and they go like this. So I'm going to call this, let's call it PA, I want to give it a name, so I'm gonna. But anywhere along that dotted line, it's at the same, that PA, that pressure PA. So if I were over here, right here, right there on that saturated liquid line, then I would be at that pressure PA. If I were right here, I'd still be at that pressure PA. I'd just be at a different temperature, right? So you can see if I'm at that particular pressure PA and it's saturated, it's somewhere in that two-phase region, there is only one possible temperature that it could be at, and let's call that TA. And then we call that temperature the saturation temperature, Tsat, at whatever pressure we're talking about. So in this case, we're talking about PA. And then I could also, there are other lines, there's, you know, lots of lines of constant pressure that I could draw. So maybe I draw one up here. Go. Tails kind of go up like this. We'll call this PB. Anywhere along that little line, that little dotted line, it's a constant pressure PB. And then the temperature that corresponds with that PB in that two-phase region, let's call that TB. And that's just going to be, I need that a little bit smaller. That's going to be the saturation temperature, Tsat, at that particular pressure. All right, and we could do the same thing on that PV diagram because there are lines of constant temperature there as well. So let's draw those. And they look really similar, but the tails are flipped, meaning that it goes kind of like this. So straight across horizontally and then down. So let's call this TA. And call this PA. So that pressure is that is the saturation pressure at TA. It is the only pressure that the water could be at and be saturated at temperature TA. You'd also throw another one over here. Let's call this TB, right? Well, this pressure right here, we'll call it PB. This would be Tsat at TB. And the relationship between like TA and TB is kind of what you would think, right? TB is bigger than TA. Same thing with the pressures over here. PB is bigger than PA. Right? So with that being said, let's kind of go back here to our next kind of fill in the blank. So if the pressure is constant during a phase change, the temperature is constant too. Everything that's under that dome it's a phase change. So right, so you could see that if you look at let's look at the TV diagram. So if I look at that dotted line corresponding to PA, in that two-phase region, doesn't matter where I am in that two-phase region, as long as I'm at that PA, there's only one possible temperature I could be at, and that would be the saturation temperature. So the temperature is constant. And then at a given pressure, the temperature at which that phase changes occurs is called the saturation temperature at that particular pressure. Same thing over here. At a given temperature, the pressure at which the phase change occurs is the saturation pressure. Constant communication with your kids is, or the ability for your kids to constantly communicate with you is perhaps not the best thing. You know, who doesn't want to come home from school? That's the kind of messages I'm getting right now. Okay. So if you watched through video 1.7, it talks about how you can use those PV and those TV diagrams and look at lines of constant temperature and pressure to figure out, based on that information, what phase you're in. And this page right here gives you kind of the snapshot of, or the summary of all that stuff. And if you can memorize this, this will help you. Okay, so it's important to be able to reason out what phase you're in using those PV and TV diagrams. But on a regular basis, if you memorize this, you're golden. Okay. All right. So, but before we start looking at these guys, let's look at our thermodynamic tables. So, if I look at the first page of the thermodynamic table PDF packet. So I've got saturated water, A2 is properties of saturated water, temperature table, table A3, properties of saturated water, pressure table. And it's the exact same information in each of those tables. And there's also, you can see at the bottom here, I've got underlined, there's tables in English units as well. But looking at A2 and A3, so these are properties that show you properties for water if it's under the dome or on the dome. So let's go look at them and see what kind of information is there. All right, so if I look at table A2, there's a lot of information here that's, we don't really need at this point, but let's kind of look at it. So once again, I'm thinking about, the vapor dome. It is everything on the dome or under the dome. So if I'm at that location, if that's the phase of my water, then these are the tables that I'm going to use. All right. So if let's look at 10 degrees Celsius. At 10 degrees Celsius, the saturation pressure is 0.01228. Okay, so I'm going to draw that up here. Let's say this is 10 bar. And the saturation, I'm sorry. Let's make that TB. Sorry about that. So 10 degrees Celsius, and the saturation pressure be anything along this line right here. So this would be 0.01228 bar. Okay. Then you've got this guy and this guy. So the V sub F is the specific volume associated with the saturated liquid portion of that two-phase mixture. So if you had 100% saturated liquid in that two-phase mixture, you'd be right on that saturated liquid line. And that would be this guy right here, the V sub F value, which is this number right here. And you note that it's already been multiplied by 1,000, so it's not 1.0004 meters cubed per kilogram. It's actually 0.001004 units or meters cubed per kilogram. And then if we look at this guy right here, that V sub G is the specific volume associated with the saturated vapor portion. So that specific volume would be 106.379 meters cubed per kilogram. So you could see if I were at 10 degrees Celsius and I had a specific volume, the water had a specific volume above 106.379, then, my state would be out here in the superheated region. If it were below 0.001004, meters cubed per kilogram, it'd be over there in the liquid region. And so that's sort of where these rules, where are we? These rules over here come from. So if your specific volume is less than the V sub F at a given temperature and pressure, then you know you're compressed. If it's above, then you know you're superheated. And if it's between those values, then you know you're somewhere under the dome, right? If your V sub F is equal to your specific volume, then you know it's a saturated liquid, right? If the specific volume is equal to that V sub G, it's a saturated vapor. Okay. So that's table A2. We also have property data for saturated water, but it's organized by a pressure instead, and that's table A3. Same data, and you can use either one. It doesn't really matter. It's just organized a little bit differently and might be a little bit more convenient. So table A3, all organized by pressure. So if I sort of drew this on a there we go, PV diagram. So I'm going to pick something I can zoom into. So if I were at 0.08 bar, let's just say 0.08 bar. Well, I know that the corresponding temperature that I was at, draw a little line of constant temperature. Remember, the tails are flipped. So here, my temperature would be 41.51. And then this guy would be our V sub F value. So this guy right here, and this data point would correspond to this 18.103. So this is 0.001084 meters cubed per kilogram, and then this would be 18.103 meters cubed per kilogram. Okay, so that's all if it's saturated. Now, if you figure out, based on those rules that we had a second ago, if you figure out that you're superheated, right? Say you know that your water is at 0.08 bar, but your specific volume is above that 18.103. You know you're superheated based on those rules, and you go to your superheated tables. So your superheated tables are table A4. I clean that up. And so you just need to go, you see it's organized sort of in chunks or blocks of pressure. So you would just go to the corresponding pressure block and get your data from there. Conversely, if you figure out that it's compressed, we have compressed tables as well for water, and that's table A5. There we go. Same kind of thing. It's organized in blocks of pressure. Easy peasy. All right, so let's go back over here. So those are our rules. Make sure that you watch those videos because it goes into some pretty good detail about, why those rules are the way that they are. All right, so problem 7. At what temperature does water condense? At 30 kilopascals. And I'm going to go ahead and write that as not 30 kilopascals, but 0.3 bar because my tables are written in terms of bars. But we want to know what temperature does it condense at and what temperature does it boil at. And really this is the same question, it's just phrased in two different ways. It's what temperature does it undergo a phase change between a liquid and a vapor at 30 kilopascals or 0.3 bar, and what we're looking for is the saturation temperature. So Tsat at 0.4. All right, so under my givens, I've went ahead and written down this for you, but keep in mind on a test, you would need to make sure that you define all your variables and stuff, define what you're trying to find, but just for time's sake, I've written these down. So I've noted that we've got water It's at 0.3 bar, and we're looking for the saturation temperature at 0.3 bar. And there's not really any assumptions that I need to make or that I think I need to make at this point, so I'm just going to keep on going. All right, so I need to look in my saturation tables. I can look in table A2, or I can look in A3. But I'm going to look in table A3 because table A3 is organized in terms of pressure, and that's what I've got. I've got pressure. But once again, it's the same information, just one table might be a little bit more convenient to use than the other. So what I've done, just so you can mark on your notes and keep everything organized and tell the story for yourself very well, is I've sort of have a snippet of table A3 at the bottom there that you can mark up. So we are at, I forgot already, I need my, there we go, 30 kilopascals, so 0.3 bar. So we are at 0.3 bar in table A3. And I can see the saturation temperature is 69.10 degrees Celsius. And that's the temperature, the only temperature that water could be at and be saturated, be boiling or condensing, and still be at 0.3 bar. So 69.10 is what I've got. So my temperature is Tsat at 0.3 bar, and it's 69.1 degrees Celsius. There we go. Perfect. All right, let's go to the next guy. Problem 8. We want to know the specific volume of saturated liquid water at 75 degrees Celsius. So I've noted that it's water, I've noted the temperature, and I've also noted that it's saturated liquid water. So that gives me an idea of where this thing is. So like if I put things on a TV diagram, and that's not what it's asking me for, but I'm just going to go ahead and show you. So if we're at 75 degrees Celsius, and I know that it's a saturated liquid, that means it's on this line, this side of the dome here. And so that's it. That's the location of the state of my water. And so what I'm going to be looking for is this specific volume. And remember, this is the specific volume that is associated with the saturated liquid portion. So it's going to be, I'm looking for the V sub F at 75 degrees Celsius. So I can look in table A2 or table A3, because that's going to give me property data for saturated water, but probably table A2 is going to be the one that I need because it's organized by temperature. So if I kind of scroll down here at the bottom, I'll see that that's already kind of highlighted for me. So looking in A2, 75 degrees Celsius. If I really wanted, I could get the saturation pressure. Maybe I'll go ahead and put that on there. I know that's not what I need, but I'm going to put that on there just to kind of have it. 0.3858. 858. But I don't need that. I actually just need this. Okay. So it's not 1.0259. That's already been multiplied by 1,000. It's actually 0.0010259. Go. And so that's the answer. Okay. All right, so problem 9 is going to ask us what is the specific volume of saturated water vapor? So saturated water vapor at 10 bar, and we want to find the specific volume. So this is, you know, kind of similar. Instead of drawing illustrating this, I guess, on a TV diagram, well, I'm given the pressure, so I'm going to put it on a PV diagram. Right. So I know that it's a saturated water vapor, so it's going to be somewhere on this side of the dome, and I'm at 10 bar. And so it's like if I kind of just follow that over, that's going to be the location of my data point. And so this specific volume here, well, it's the specific volume that's associated with the saturated vapor portion of this two-phase, or the saturated water. So V sub G at 10 bar. And I can look this up in table A2. Those are saturated tables for water organized by temperature, or A3, which is organized by pressure. And I just happen to know pressure, so that's the one I'm going to look at. Okay. All right, so I've got it down here at the bottom. We're at 10 bar. 10 bar. So I can see, well, there's my saturated, my saturation temperature, right? So I know at 10 bar, if it's saturated, it's a saturated vapor. I know that the temperature is 179.9 degrees Celsius, if I cared about that. And then I'm looking for the specific volume of the saturated vapor portion, so 0.1944. So 0.1944 meters cubed per kilogram. And so that's it, right? I've answered the question. Once again, kind of noted that the temperature was, the saturation temperature, it's 179.9 degrees Celsius. So just, I mean, not important for answering this question here, but just kind of giving you an idea of how all the information fits together. Okay. So problem 10 is going to ask us, is it possible for water to boil at 0.04 bar and 35 degrees Celsius? So let's go over there and see if that is possible. So I've got the substance noted, I've got the temperature and the pressure noted. And so we want to know, can the water boil? And what we're really asking is it saturated? Is that water saturated at that temperature and pressure? And if I flip back to those rules that I had, so let's go look at that. Where's that? All right. So I have a two-phase, or a saturated substance, if my temperature is equal to the saturation temperature at a given pressure, or the pressure is equal to the P sat at T. I've also got something with specific volume, but that's not, you know, my problem doesn't mention anything about specific volume, so I can't really use that to figure things out. But what I need to know is T sat at 0.04 bar, is that equal to 35 degrees Celsius? If it is, awesome. That means that yes, it's saturated, yes, it can boil, it can condense, and go through that phase change between a liquid and a gas. Another way of putting it is the saturation pressure at 35 degrees Celsius, is it 0.04 bar? All right, so I can look in A2 or A3. So I'm going to do that. And same thing, I've sort of cut out a section of A2 and A3 here at the bottom so you can mark up your notes. So got two of them. So table A3, it looks like the only possible pressure or the only possible temperature that I could be at and be two-phase, be in that saturated region, water boiling, the only temperature that it could boil at would be 28.96 degrees Celsius. If it's at 35 degrees Celsius, it's no longer going through a phase change, it's in that superheated region. It's all gas. And same thing if we wanted to kind of look at things by temperature. So looking at table A2 where things are organized by temperature, at 35 degrees Celsius, the only possible pressure that we could be at and be saturated is 0.05628 bar. So our pressure is 0.04 bar, which, right, is not the same thing. So what we found is that the saturation temperature at 35, I'm sorry, at 0.0 bar was, what was that, 28.96. Well, our temperature is 35 degrees Celsius. So our temperature is greater than the saturation temperature. And if you look at those rules that we were flashing back to, it just means that it's superheated. Same thing with the pressure. We could tell by the pressure. The saturation pressure at 35 degrees Celsius, which if we look down here, what was that? 0.05628. 0.05628 bar. Well, our pressure is 0.04 bar. So our pressure is less than that saturation pressure. And by those rules, tells us the exact same thing, that it's superheated. So you can tell by, by either one of those justifications that it's superheated. And if I wanted to know property data, I would need to go to the saturation or to the superheated tables, table A4. All right, so got 8 more minutes. 8? Yes, 8 more minutes. So we need to determine the phase or the phases in a system containing water. And we've got 4 different scenarios where we're given a pressure and temperature. We need to figure out the phase, and then we need to draw the location if we can on a PV and a TV diagram. So I've cut out parts of those tables. I would just keep in mind this is, me cutting out those parts of the table is really just to help you keep your things organized so that when you go back and review, it's really easy to see, to tell yourself the story of how we calculated these things. But once again, it's going to be up to you to kind of flip through and make sure that you can find that data. So yeah, and I won't on the other units, I don't cut out these, but just while we're learning to read the tables. So we need to figure out the phase. So for A, need to find the phase. Always, you're going to go to the saturated tables, saturated water tables in this case, but you're going to go to the saturated tables and use the property data to determine the phase. Okay, so your first stop is those saturated tables. It doesn't necessarily mean that you're right away saying it's saturated. You're just going to be using the information there to figure out what phase it's in. If it is saturated, great, you're in the right place. But if it's not, then you need to go to the other set of tables. So once again, I've got table A2 and A3. Saturated tables are just organized different ways. Table A2, it's organized by temperature, and it's organized really in discrete kind of temperature values. So I'm at 179.9 degrees. So, really I'd have to interpolate if I really wanted to get accurate, but it'd be right there. So you could see, yeah, probably about 10. We'll talk about interpolation, but not today. However, if I look over at A3, I do have this nice discrete value. So at 10 bar, you can see that the only temperature that water can be and be saturated is 179.9 degrees Celsius. So our saturation temperature at 10 bar is equal to our temperature. You know, so we can say that it is saturated. And next thing I needed to find, draw it on a PV diagram and a TV diagram. It's the first one I forgot already. PV, doesn't really matter. So here's our PV diagram. Here's our TV diagram. Okay, so the PV diagram, that vapor dome, it's a little shorter and squatter. TV diagram is prettier. But it doesn't really matter. I mean, just as long as you have a dome drawn, that's fine. All right, so 10 bar. This was 179.9 degrees Celsius. And if I wanted to draw, you know, a line of pressure corresponding to this, well, this temperature is 179. And same thing, I could, oops. What did I do? My tails are wrong. Gotta go the other way. Okay. So anywhere along that line, the temperature is 179.9 degrees Celsius. And then I could draw a line of constant pressure like this. So anywhere along there, our pressure is 10 bar. Now, here's the case. We know it's saturated. However, we'll note that the temperature and pressure are not independent. I think it's E-N-T. I think I spelled it with A-N-T before, so sorry about that for anybody that caught that. But temperature and pressure, they're not independent of one another. So we cannot, I guess we'll say fully fix the state. I mean, we can tell what phase is in, but we don't know, I can't put a, oh, thank you, it is wonderful drawings. We can't fully fix the state because we can't put a dot right where the, right where that state is. So really all I can say is that I am somewhere in this region. Right, might be right on the dome, but might also be somewhere in between. So that's really all I can say for this problem. Yeah. All right. So we really only have 2 more minutes left, so I will go ahead and stop there. And if you have questions, as always, feel free to just interrupt me. If you raise your hand, I'm probably not going to see it, to tell you the truth. It doesn't ding at me or anything. So just please interrupt me. I won't be upset. Hey. All right. So I will see you guys on Friday, and then keep in mind there are office hours tomorrow with Josh. I think Josh is going to handle them tomorrow, okay? All right, y'all have a wonderful day, okay? Thank you.
Thank you. Have a good day.
Thank you, you too.